talking about parallel programming route, exactly what we are doing, and more precisely, or a bit more elaborate, why we are doing that. So you might already have noticed if you bought a laptop recently or a machine recently, there has been some change. You didn't buy a laptop with 5 gigahertz or something, but you bought maybe a netbook, a small one with 2 cores, or you have a big workstation in your, under your desk which has 12 or 24 cores, or as a lab we even have a very embedded system with a really small tiny CPU which actually has 64 cores. So there's a major shift here. Tia was already talking about. And the problem here is we hit some physical boundaries. So 5 years ago we hit some peak. There were CPUs, Intel was selling CPUs with 3.8 gigahertz, and now it's marginally less, but actually we have 6 cores in our standard computer they are selling. And the reason is these things are just producing too much heat. So if you go beyond 4 gigahertz, it's becoming too complex to get away all the heat you're producing, the power you're consuming is really transformed into heat. And well, what they are doing is basically they try to find another way to make the computers faster without producing too much heat. And so they try to keep the power stable they use, and by that, or to achieve that goal, they have to reduce the frequency. So actually everything is slightly getting slower, but on the other hand, we are getting more cores. And well, that brings us to the problem of the software engineering. And well, for the last few years, we had like 50% more performance every year, and that's over now. And now we have every year like 50% more cores on our CPUs. And that implies that we don't actually have more performance every year like we used to have for the last 40 years. So we actually run into some trouble. And that's a good example of what's happening in software also. So you have these kind of gridlocks in the real world, and that's just showing that it's hard to deal with concurrent parallel systems in general. And the mainstream approach we have today, that's basically you try to make your things safe. So if you're able to program, if you have ever programmed, you have used whatever language, I don't know, but all these languages, they usually have ways to express parallelism, and if you have parallelism, then you run in situations where you want to modify certain states, and that can happen in parallel. And that's really hard. So people today, the real experts, they do that to build operating systems, they do that to build databases or virtual machines or whatever, but that's really hard. And the mere models which are building actually the valuable stuff on top, the daily applications you use, right, from application server, for them is just too hard. Because the problem is, if you build with these mechanisms a system, you really have to, the whole view of the whole, like the city here to avoid gridlocks, and that's really just for the expert. Because you need to know all the modules in the system and how they interact. And if you come to build business applications, you want to solve your business problem. You want to solve the problem of your customer. And if you have to handle all these blocks, that's really distracting from the actual program. And that's why we are looking for better solutions than these current mainstream approaches. So what we are doing in the lab is we are looking into better languages. We are looking into smarter runtimes, which allow us to use the available hardware efficiently. And then we are looking into how we can actually co-evolve the languages and the runtimes to come to a point where these not just coexist, but actually integrate and run efficiently. And as I already said, one of the big problems is a shared mutable state. So you have Hannibal Lecter here. Here's a real evil problem. And yeah, every time you have this kind of situation in your program, you have a resource and multiple activities are working with it. You have to lock it. And the smart people in the 70s came up with ideas of vectors. So here's still Hannibal Lecter, but the shared state that's just inside. So the evil is just inside. And the actors are communicating via message passing, and that's the idea behind that kind of language, actual languages. But that's not the solution for everything. So we have all these legacy systems out there. We cannot just use new languages for them. And then we have certain kind of problems which are really naturally expressed in a sequential manner. And here the people have been doing research for the last 40 years. to do automatic parallelization. And that's kind of considered the holy grail. So they did parallelize loops and all kinds of things, and they run a whole problem. Well, we are also looking into that, but we are not looking for the holy grail, but for something more practical. So we are even interested in smaller speedups. And that brings me to the core evolution. So we want to look into, or we are looking into, how we can use these new languages and these ideas to make things faster on the existing today's hardware, and we are co-evolving our virtual machines with respect to the hardware on the one hand, to the language ideas we have at the lab and which are out there to handle shared state, for instance, and the idea is to automatically parallelize code, and that results in a number of artifacts. Here at the left, so there's real work in we have Manycore, we'll talk about later. We have the raw VM, which is a Manycore virtual machine running on the embedded system I showed you. Then we have Hector scheme, which is basically Charlotte's thesis. You can follow the thesis presentation on the 20th, right? And well, there are a lot more things going on. And there are people you can talk to if you